Imagine standing on the surface of a world where the air itself could crush you like the depths of Earth's deepest ocean, where the temperature is hot enough to melt lead, where clouds of sulfuric acid drift across a sky that glows a sickly orange-yellow, and where a single day lasts longer than an entire year. This is Venus, our sister planet, the second world from our Sun, and quite possibly the most hostile environment in our inner solar system. Now, here's a question that might sound absolutely insane. What if, instead of dreaming about Mars with its rusty deserts and frozen valleys, we decided to transform Venus into a second Earth? What if we chose hell over the cold silence of the red planet? For decades, humanity has gazed at Mars with longing eyes, imagining domed cities and terraformed landscapes where children play beneath pink skies. We've sent rovers, orbiters, and landers. We've mapped every crater, analyzed every rock, and planned missions that would bring the first human footprints to Martian soil. But while we've been obsessed with Mars, Venus has lurked in the background, dismissed as impossible, as too extreme, as the planet that ate Soviet spacecraft for breakfast. Here's what most people don't know. Some of the world's most brilliant planetary scientists believe that Venus, despite its nightmarish conditions, might actually be the better candidate for terraforming. In fact, in many ways, it might be easier than Mars. Does that statement shock you? It should. Let me explain why this counterintuitive idea isn't just possible, but might represent humanity's best chance at creating a true second Earth. Before we dive into the mechanics of transforming hell into paradise, let's understand exactly what we're dealing with. Venus is approximately the same size as Earth, about 95% of Earth's diameter, with roughly 80% of Earth's mass. It's the closest thing to an Earth twin in terms of basic physical properties that we know of in the entire universe. It orbits closer to the Sun than Earth, at about 72% of our distance, which should make it warmer, but not apocalyptically so. So what went wrong? Why did Earth become a vibrant blue oasis while Venus transformed into what scientists call a runaway greenhouse? The answer to this question is both fascinating and terrifying because it reveals how fragile planetary climates actually are. Venus's atmosphere is the culprit behind its hellish conditions, but also, paradoxically, might be the key to its transformation. The Venusian atmosphere is 92 times denser than Earth's at sea level. Think about that for a moment. If you could stand on Venus's surface, the atmospheric pressure would be equivalent to being a kilometer beneath Earth's oceans. This crushing blanket of gas is 96% carbon dioxide, with clouds of sulfuric acid floating between 45 and 70 kilometers above the scorched surface. The greenhouse effect created by all this carbon dioxide has pushed surface temperatures to a lead-melting 470 degrees Celsius, or 878 degrees Fahrenheit. There's no liquid water anywhere on the planet. No rain except for virga of sulfuric acid that evaporates before hitting the ground. No relief from the crushing heat and pressure. Here's where it gets even stranger. Venus rotates on its axis incredibly slowly and in the opposite direction to most planets in our solar system. One Venusian day lasts 243 Earth days. And bizarrely, a Venusian year is only 225 Earth days long. This means a day on Venus is actually longer than its year. The planet essentially rotates backward, though scientists debate whether it flipped over or always rotated this way. This retrograde rotation creates virtually no magnetic field, meaning the solar wind strips away atmospheric particles directly. Despite this constant loss, the atmosphere remains incredibly dense because volcanic activity may be replenishing it, though this remains hotly debated among planetary scientists. So why would anyone in their right mind choose this apocalyptic nightmare over Mars? Mars, after all, seems so much more approachable. It has polar ice caps, seasons, a day that's remarkably similar to Earth's at 24 hours and 37 minutes, evidence of ancient rivers and lakes, and temperatures that, while cold, occasionally creep above freezing at the equator. The Martian atmosphere is thin enough that it barely registers, about 1% of Earth's atmospheric pressure, composed mostly of carbon dioxide. The surface is bathed in radiation because Mars lacks a strong magnetic field and has virtually no atmosphere to protect it. It's cold, with average temperatures around -63 degrees Celsius. And the soil contains perchlorates that are toxic to human biology. But at least robots can survive there for years. At least we can imagine walking on the surface in a spacesuit. Venus, by contrast, has destroyed nearly every probe we've sent, with Soviet landers surviving on the surface for a maximum of just 127 minutes before succumbing to the extreme conditions. Yet here's the critical insight that changes everything. Mars is missing something fundamental that Venus has in abundance. Mars has lost most of its atmosphere to space over billions of years, and it has insufficient gravity and no magnetic field to hold onto a thick atmosphere if we created one. Venus, on the other hand, has too much atmosphere, but it has the gravity to keep it and the size to maintain geological activity. Mars is a dead world, geologically speaking, with a frozen core and no tectonic activity. Venus might still be geologically active, with possible evidence of recent volcanism. Mars is too small, too dead, too far from the Sun. Venus is too hot, too pressurized, but it's alive, it's massive enough, and it's closer to the energy we need. Ask yourself this: is it easier to add something that's missing or to remove something that's excessive? Is it easier to warm up a freezer or cool down an oven? The answer isn't as obvious as it seems because the scale of planetary engineering makes intuition unreliable. When terraforming advocates compare Mars and Venus, they're essentially asking whether we should resurrect a corpse or heal a patient with a dangerous fever. Both sound impossible, but the physics and engineering involved are remarkably different. Let's travel back in time for a moment to understand how Venus became such a cautionary tale. Billions of years ago, Venus might have been habitable. Recent climate models suggest that Venus could have had liquid water oceans for perhaps 2 to 3 billion years after its formation. Imagine that, a blue Venus with crashing waves, rainfall, possibly even life. What happened? The leading theory involves a runaway greenhouse effect triggered by the planet's proximity to the Sun and possibly massive volcanic eruptions. As the young Sun gradually brightened over geological time, Venus received more solar energy. This caused more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, trapping more heat, which caused more evaporation, in an unstoppable feedback loop. Eventually, Venus's oceans completely evaporated. The water vapor rose high into the atmosphere where ultraviolet radiation from the Sun split the water molecules into hydrogen and oxygen. The light hydrogen escaped to space while the oxygen either escaped or bound with surface rocks. The carbon dioxide that on Earth would be locked in limestone and carbonate rocks remained in Venus's atmosphere because there was no water to facilitate the carbonate-silicate cycle that regulates Earth's climate. Volcanic eruptions continued adding more carbon dioxide, with nothing to remove it. The atmosphere grew denser and hotter in a vicious cycle that transformed Venus into the hellscape we observe today. The Soviet Union's Venera program gave us our first real glimpses of this alien world. Between 1961 and 1984, the Soviets launched a series of increasingly sophisticated probes to Venus. The early attempts failed, but Venera 4 through 8 began returning data from the atmosphere. Venera 7 became the first spacecraft to successfully transmit data from another planet's surface in 1970, surviving for 23 minutes. Venera 9 and 10 sent back the first photographs from Venus's surface in 1975, revealing a landscape of flat rocks beneath the dense orange haze. These images are haunting, a desolate expanse of fractured basalt stretching to a horizon hidden by the thick atmosphere, lit by diffuse sunlight that filters through the clouds, everything rendered in shades of orange and brown. It looks simultaneously ancient and apocalyptic, like the aftermath of some cosmic catastrophe. The Venera 13 and 14 missions in 1982 sent back color photographs and analyzed the surface composition, finding basaltic rock similar to Earth's volcanic regions. Venera 13 survived for 127 minutes, a record that still stands. Think about that. Human engineering created a machine that could function for just over 2 hours in conditions that would instantly kill any known life form and destroy most materials we've ever created. The probes revealed wind speeds of about 1 meter per second at the surface despite the hurricane-force winds in the upper atmosphere, moving the thick air like slow molasses. Every piece of data returned by these missions reinforced Venus's reputation as utterly inhospitable. Yet even as these missions painted Venus as impossible, a few visionary scientists began asking a radical question. What if we could change it? The father of terraforming as a serious scientific concept was astronomer Carl Sagan, who in 1961 published a paper proposing the seeding of Venus's atmosphere with algae that would convert carbon dioxide into oxygen. This early proposal was based on incomplete data about Venus's conditions and wouldn't work with what we now know, but it sparked serious scientific discussion about planetary engineering. Later, in 1973, Sagan proposed a different approach for Mars, but the seed was planted. Perhaps planets need not remain as we found them. The modern conception of Venus terraforming began taking shape in the 1990s when scientists started seriously modeling the physics involved. They realized something profound. Venus's dense carbon dioxide atmosphere, the very thing that makes it uninhabitable, could be converted into something useful. Carbon dioxide is made of carbon and oxygen. If you could sequester the carbon and release the oxygen, you'd simultaneously reduce the greenhouse effect, lower temperatures, decrease atmospheric pressure, and create breathable air. It's an elegant solution in theory, but the scale is almost incomprehensible. We're talking about processing an atmosphere that contains about 500,000 times more carbon dioxide than Earth's entire atmosphere. Here's where competing proposals emerge, each with different timescales, technologies, and philosophies. The first major approach involves what scientists call atmospheric removal or atmospheric processing. Imagine factories, either floating in the upper atmosphere or positioned on the surface, that would chemically break down carbon dioxide. One proposed method involves reacting carbon dioxide with calcium or magnesium delivered from asteroid mining to form carbonate rocks, essentially accelerating the natural carbonate silicate cycle that failed on Venus. Another approach suggests using engineered microbes, designed to survive in the Venusian atmosphere, that would convert carbon dioxide into organic compounds that would rain down and be buried, sequestering the carbon. The problem with these approaches is time. Even with millions of atmospheric processors working continuously, removing enough carbon dioxide to significantly alter Venus's climate would take thousands of years. Some estimates suggest tens of thousands of years. That's not necessarily a deal-breaker. If you're thinking on civilizational timescales, humanity has existed in recognizable form for thousands of years already. But it does mean that whoever started the project wouldn't live to see its completion, nor would their children, grandchildren, or great-great-great-grandchildren for hundreds of generations. You'd be building a project for humanity's future, not your own. This is where the second major approach comes in, and it's far more dramatic: solar shading. What if, instead of slowly processing the atmosphere, we simply blocked enough sunlight to cool the planet down rapidly? The concept involves positioning massive solar shades at the Venus-Sun Lagrange point, the gravitational balance point between Venus and the Sun. These shades wouldn't be solid structures, but rather swarms of small reflective spacecraft, or even just clouds of reflective dust, positioned to cast Venus into partial shadow. The calculations suggest that blocking about 90% of sunlight would cool Venus enough for carbon dioxide to begin condensating out of the atmosphere as dry ice, which would then fall to the surface and could be buried or processed. Picture this: Venus gradually dimming as the solar shades deploy, the eternal scorching heat beginning to subside for the first time in billions of years. The upper atmosphere starts to cool, and dry ice begins to snow from the sky, something that has never happened in Venus's observable history. The surface temperature drops over decades from lead-melting heat to something merely boiling, then to something hot but survivable with proper equipment. The atmospheric pressure decreases as carbon dioxide is removed from the air. This process could potentially transform Venus in centuries rather than millennia, but it requires enormous infrastructure in space and constant maintenance of the solar shades. The truly wild part: once Venus cools sufficiently, you could introduce water. Hydrogen from gas giant moons or comets could be redirected to crash into Venus, bringing the water that the planet lost billions of years ago. As Venus cools below 100 degrees Celsius, liquid water could exist again on the surface. With water and a cooler climate, you could potentially trigger the carbonate-silicate cycle, where water and carbon dioxide react with rocks to form carbonates, further removing carbon dioxide from the atmosphere. Rain would fall on Venus for the first time in perhaps 2 billion years, initially as toxic acidic rain due to the sulfuric acid in the clouds and dissolved carbon dioxide, but gradually becoming less hostile as the atmosphere changed. Now here's a question for you to consider. If we had the technology to terraform a planet, do we have the right to do it? Venus, as far as we know, is completely sterile, but we haven't explored enough to be absolutely certain. What if microbial life exists in the temperate cloud layers, 50 to 60 kilometers above the surface, where temperatures are surprisingly Earth-like and pressure is similar to Earth's surface? Some scientists have speculated about this possibility, pointing to unexplained patterns in ultraviolet observations of Venus's clouds. If life exists there, even simple microbial life, would terraforming Venus constitute the greatest genocide in history, the deliberate destruction of an entire biosphere? Or would we have an obligation to preserve and study it while still transforming the planet? These aren't just philosophical questions. They have profound ethical implications that we need to grapple with before we develop the capability to act. Let's examine the cloud layer idea more carefully because it reveals something remarkable about Venus. Part of the planet is already habitable, just not the part we usually think about. At an altitude of 50 to 60 kilometers above Venus's scorching surface, atmospheric pressure is about 1 bar, the same as Earth's sea level. Temperatures hover around 0 to 50 degrees Celsius, genuinely comfortable for human habitation with appropriate life support. You could walk around in a suit requiring no pressure support, just oxygen and protection from sulfuric acid. Scientist Jeffrey Landis and others have proposed that before terraforming Venus's surface, we could establish floating cities in this temperate zone, habitats filled with breathable air that would actually float in Venus's dense carbon dioxide atmosphere like helium balloons on Earth. Imagine vast transparent spheres drifting through Venus's upper cloud layers, containing gardens, habitats, laboratories, and eventually cities, held aloft by the simple fact that oxygen and nitrogen at reasonable temperatures are lighter than the carbon dioxide atmosphere around them. These cities would harvest solar energy from the abundant sunlight above the clouds, extract water and sulfur compounds from the clouds themselves, and potentially manufacture supplies from the atmospheric carbon and nitrogen. From these floating platforms, humans could orchestrate the transformation of the world below over centuries, watching as the furnace-like surface gradually cooled and changed. It's a vision straight out of science fiction, but the physics is sound. The engineering challenges are immense, but they're challenges of scale and materials, not fundamental impossibilities. This is where Venus's advantages over Mars become clearer. Mars has no equivalent to this habitable zone. Mars's entire atmosphere is too thin and too cold. On Mars, you must either seal yourself in pressurized habitats on an irradiated, toxic surface, or you must dig underground. Venus offers a middle ground, a place where you could live relatively exposed to the environment with only moderate protection. The psychological difference is profound. On Mars, you'd always be acutely aware of being sealed away from instant death. In Venus's clouds, you'd be floating free, able to see the sky and clouds even if they're alien. There's a romance to it, a sense of adventure that Mars's underground bunkers can't match. Let's talk about another crucial advantage: gravity. Venus's gravity is about 90% of Earth's. After living on Venus, you could return to Earth and readjust relatively easily. Children born on Venus would develop with bone and muscle structure nearly identical to Earth humans. Mars, by contrast, has only 38% of Earth's gravity. We don't know what effect growing up in Martian gravity would have on human development, but it's likely problematic. Bones might not develop proper density, hearts might not develop sufficient strength, bodies might elongate in ways that would make returning to Earth extremely difficult or impossible. A child born on Mars might be trapped there forever, unable to withstand Earth's gravity. A child born on Venus could theoretically travel throughout the inner solar system without medical issues. Solar energy is another massive advantage. Venus receives about twice the solar energy per square meter as Earth, and about 4 times what Mars receives. This means solar panels on Venus, or rather in Venus's clouds or in orbit around Venus, would generate far more power than equivalent installations at Mars. Power is the foundation of any terraforming effort. You need enormous amounts of energy to run atmospheric processors, maintain solar shades, manufacture materials, and support human colonies. Venus's proximity to the Sun makes this significantly easier than at Mars, where solar panels are less efficient and nuclear power becomes more necessary. Here's something most people don't realize. Venus is actually easier to reach than Mars in terms of energy requirements. Due to orbital mechanics, the delta V, the change in velocity required to reach Venus from Earth is actually slightly less than reaching Mars. Venus's orbit brings it closer to Earth than any other planet, approaching to within 40 million kilometers at its closest, while Mars never gets closer than about 55 million kilometers. This means launch windows to Venus occur more frequently, and missions could be completed faster. If we're planning to move substantial amounts of material and people to another planet, these efficiency differences add up enormously over time. But let's return to the terraforming timeline and get specific about what would actually happen if we committed to transforming Venus. The leading comprehensive proposal comes from a series of papers and analyses conducted by various planetary scientists over the past few decades. Here's how it might unfold, step by step, assuming we had the necessary technology and resources. Phase 1 would involve establishing orbital infrastructure and the first floating research stations in the cloud layer. This phase might take 20 to 50 years and would involve deploying automated mining facilities on the Venusian surface or on captured asteroids to begin harvesting materials. Simultaneously, we'd position the first solar shade elements at the Lagrange point and begin blocking sunlight. Phase 2 would span perhaps 1 to 3 centuries and would involve the rapid cooling period. As sunlight is blocked, Venus's surface temperature would drop dramatically. Computer models suggest that with 90% shade, Venus could cool from its current 470 degrees Celsius to below 100 degrees Celsius within a century or two. As it cools, carbon dioxide would begin condensating and falling as dry ice snow. Enormous automated systems on the surface would bury this dry ice under regolith or process it chemically, preventing it from sublimating back into the atmosphere as temperatures fluctuated. During this phase, atmospheric pressure would drop significantly, making the surface increasingly accessible. Phase 3 would involve introducing water and nitrogen. Venus's atmosphere is actually poor in nitrogen compared to Earth, despite having a much larger total atmospheric mass. Earth's atmosphere is 78% nitrogen, and we need nitrogen for breathable air and for biology. Water would come from redirected comets or from the ice moons of Jupiter and Saturn. The logistical challenge of moving billions of tons of ice across the solar system is staggering, but not impossible with sufficiently advanced propulsion systems. Some proposals suggest using gravity assists and ion drives to slowly move ice-rich asteroids or small moons onto collision courses with Venus over decades or centuries. Imagine standing on a floating platform in Venus's clouds during this phase, watching comets streak through the sky and crash into the surface below, each one bringing precious water and potentially nitrogen if they're sourced from the outer solar system. Each impact would release enormous energy, but with the surface already hostile and uninhabited, this wouldn't destroy anything valuable. Over time, water would accumulate. Rain would begin to fall, initially boiling away but gradually forming hot acidic pools, then lakes, then perhaps small seas. The water would begin dissolving minerals from the rocks, gradually neutralizing the acidity over geological timescales, similar to how Earth's early oceans developed. Phase 4 would involve active biological engineering. Once temperatures were suitable and water existed, we'd introduce specially designed microorganisms, perhaps based on extremophile bacteria from Earth but heavily modified to survive in Venusian conditions. These organisms would serve multiple purposes. converting remaining atmospheric carbon dioxide into oxygen, building soil from rock and organic matter, neutralizing acidic compounds, and establishing the foundation of an ecosystem. This phase would blur into Phase 5, which would be the gradual establishment of increasingly complex ecosystems over thousands of years. The entire process, from initiation to a planet with breathable air, liquid water oceans, and sustainable ecosystems, might take anywhere from 500 to 10,000 years depending on which models you follow and how aggressively we intervene. That sounds impossibly long by modern human standards. But consider, the great cathedrals of Europe took multiple human lifetimes to build, yet they were built. The pyramids of Giza have stood for 4,500 years, almost half the timescale we're discussing for the faster Venus terraforming scenarios. If humanity commits to a project on civilizational timescales, if we build institutions designed to maintain continuity across centuries, it becomes conceivable. Now let's explore the most audacious idea in Venus terraforming: changing its rotation. Remember, Venus rotates incredibly slowly and backward, creating a day longer than its year and generating virtually no magnetic field. Some scientists have proposed using carefully calculated asteroid impacts or massive atmospheric manipulation to gradually increase Venus's rotation rate over millions of years. This sounds absurd until you run the numbers and realize that while difficult, it's not physically impossible, just extremely challenging and time-consuming. A faster rotation would generate a magnetic field through dynamo action in Venus's molten core, assuming the core is indeed still molten. This magnetic field would protect the atmosphere from solar wind erosion and protect the surface from radiation, making the terraformed planet more stable over geological time. An alternative proposal suggests we don't change Venus's rotation but instead embrace the long day-night cycle. The slow rotation would create extreme temperature variations between the day and night sides unless the atmosphere was thick enough to distribute heat, which creates an interesting paradox. You'd want some atmospheric density for heat distribution and pressure, but not so much that you recreate the greenhouse problem. The engineering required to balance this would be extraordinary, potentially requiring active climate management indefinitely. Some models suggest maintaining a thicker atmosphere than Earth's, but composed primarily of nitrogen and oxygen rather than carbon dioxide, creating a high-pressure but breathable environment with smaller temperature fluctuations. Here's a mind-bending thought experiment. What if we're thinking about this wrong? What if instead of terraforming Venus to be exactly like Earth, we terraform it to be something new, a world optimized for human habitation in ways Earth isn't? With active climate management, you could potentially create a planet with no extreme weather, no hurricanes or tornadoes, no droughts or floods, just stable, managed conditions optimized for agriculture and habitation. You could design ocean and continent configurations that maximize habitable land area and minimize transportation distances. You could establish ecosystems without the parasites, pathogens, and dangerous megafauna that evolved alongside humans on Earth. Venus could become not a copy of Earth but an improved version, Earth 2.0, designed with intention rather than shaped by random evolution. Of course, this level of control raises profound questions. Who decides what Venus becomes? What ecosystems do we include or exclude? What is the moral framework for creating an entire world? If different nations or groups contribute to the terraforming effort, who owns the result? These questions might seem premature given that we're discussing events potentially centuries away, but they're worth considering now because the decisions we make about planetary protection policies, space resource utilization, and international cooperation today will shape the legal and ethical frameworks that govern these future efforts. Let's compare this more directly with Mars terraforming to understand why Venus might genuinely be the better choice. The most common Mars terraforming proposal involves releasing the carbon dioxide frozen in Mars's polar caps and absorbed in its soil to create a thicker atmosphere and trigger greenhouse warming. You might detonate nuclear weapons at the poles, cover them with dark dust to increase heat absorption, or position orbital mirrors to melt the ice. The problem is that even if you released all of Mars's accessible carbon dioxide, you'd only achieve about 7% of Earth's atmospheric pressure. Not enough for people to walk around without pressure suits, and not enough to significantly warm the planet. You'd need to import massive amounts of atmosphere from elsewhere, perhaps from the moons of Jupiter or Saturn, or from comets, similar to what we discussed for Venus, but on an even larger scale because you're starting from almost nothing. Mars lacks the gravity to hold onto a thick atmosphere over geological time. Calculations suggest that a terraformed Martian atmosphere would be stripped away by solar wind over tens of millions of years without a magnetic field to protect it. This is actually a relatively short timescale geologically, meaning you'd need to continuously replenish the atmosphere or somehow reactivate Mars's magnetic field, which would require reheating the planet's core, a challenge so enormous it makes everything else we've discussed seem trivial. Some scientists have proposed positioning a powerful artificial magnetic field generator at Mars's L1 Lagrange point to deflect solar wind, essentially giving Mars an artificial magnetosphere. This is theoretically possible, but requires maintaining this massive infrastructure indefinitely. Water on Mars is another challenge. While Mars has significant water ice, it's frozen in the soil and at the poles, and liquid water is unstable on the surface due to low atmospheric pressure. Even if you warmed Mars and thickened its atmosphere enough for liquid water, you'd need to import more water to create oceans comparable to Earth's. The amount of infrastructure required starts to look similar to Venus terraforming, but you're working with a smaller planet with less gravity and less solar energy, making every step harder. Here's the critical comparison. Mars terraforming requires adding massive amounts of material the planet lacks: atmosphere, water, heat, while Venus terraforming requires removing or transforming what's already there. Both are enormous undertakings, but the physics of removing or transforming existing material might actually be more favorable than importing material from across the solar system. Venus has too much of almost everything. Mars has too little of almost everything. Venus is too hot. Mars is too cold. Venus has too much atmosphere. Mars has essentially none. In both cases, we need to establish equilibrium, but the methods and challenges differ profoundly. Now, let's discuss something that rarely gets mentioned in discussions of planetary terraforming: the timeline advantage of starting with Venus cloud cities. Unlike Mars, where you must establish surface bases in harsh conditions from day one, Venus allows you to create comfortable, sustainable habitats in the cloud layer while simultaneously working on terraforming the surface below. This means you could have thriving off-world human populations, potentially numbering in the millions, within a few centuries, long before the surface is ready for habitation. These cloud-dwelling Venusians would have the resources, expertise, and motivation to continue the terraforming project across generations. They wouldn't be dependent on Earth for survival. They'd be genuinely independent, with their own economy based on solar energy, atmospheric mining, and eventually trade with Earth and other worlds. This creates a very different dynamic than Mars colonization. Mars colonists would be struggling against their environment constantly, living in sealed habitats, probably underground, very dependent on Earth for supplies until they could establish robust industrial capabilities. The psychological and social dynamics would be more similar to Antarctic research stations or submarines, controlled, enclosed, and isolated. Venus cloud colonists would live in vast floating structures with views of clouds and sky, in near-Earth gravity, with abundant solar power. The psychological difference might be profound. One group would be sealed away in bunkers on a dead world. The other would be pioneering a new form of human habitation, cities in the sky, while actively transforming the world beneath them into something new. Let's talk about something that will determine whether any of this actually happens: economics. Terraforming any planet would be staggeringly expensive, quite likely the most expensive undertaking in human history, potentially consuming a significant fraction of global GDP for centuries. What's the economic case for doing this? The obvious answer is that eventually, Earth will either become less habitable due to climate change, resource depletion, or other factors, or human population will grow beyond Earth's carrying capacity, or will simply want the space and resources of multiple worlds. But these are long-term, existential motivations that don't generate quarterly profits. The economic case for Venus specifically might be stronger than for Mars. Abundant solar energy could power enormous manufacturing facilities producing goods for export to Earth, the Moon, and Mars. The high gravity would allow for industrial processes that wouldn't work as well in Martian or lunar low gravity. The shorter travel time to Earth compared to Mars means goods could reach Earth markets faster. Venus's clouds contain sulfuric acid, which could be processed for sulfur and oxygen, both valuable resources. The atmospheric carbon could be harvested and combined with other elements to manufacture advanced materials like carbon fiber, nanotubes, or diamond. Some visionaries have proposed that Venus could become the industrial powerhouse of the inner solar system, manufacturing everything from spacecraft to solar panels to advanced materials, all powered by limitless solar energy. Here's something fascinating. Several recent discoveries have reinvigorated scientific interest in Venus. In 2020, a team of scientists announced the possible detection of phosphine gas in Venus's atmosphere. Phosphine is a molecule that on Earth is associated with biological processes or industrial production, and there's no known abiotic process that should produce it in Venus's atmospheric conditions. The announcement was controversial, with other scientists questioning the detection and proposing alternative explanations. Subsequent observations have been inconclusive, with some confirming trace amounts and others finding nothing. Whether or not phosphine exists in detectable quantities, the debate has reminded the scientific community that we don't understand Venus nearly as well as we should. This potential biosignature, even if ultimately explained by unknown chemistry rather than life, raises the stakes for Venus exploration. If there's even a small chance that life exists in Venus's clouds, we need to send missions to investigate before we commit to terraforming. Several proposed missions are in various stages of development. NASA's Da Vinci mission is planned to drop a probe through Venus's atmosphere, analyzing its composition as it descends. The Veritas mission would map Venus's surface in unprecedented detail using radar. Russia has discussed Venera-D, a successor to the Soviet Venera program. India's space agency ISRO has proposed Chandrayaan-1, an orbiter mission. Private organizations like Rocket Lab have announced plans for Venus missions. We're potentially entering a new era of Venus exploration that could revolutionize our understanding of the planet. Imagine what we might discover. Perhaps we'll find definitive evidence of current or past life. Perhaps we'll discover that Venus's geology is more active than we thought, with ongoing volcanism that would affect terraforming plans. Perhaps we'll find unexpected resources or conditions that make terraforming easier or harder than current models suggest. Each discovery would reshape our approach to the planet. What if we found evidence that Venus was habitable more recently than we thought, perhaps as recently as 700 million years ago, as some models suggest? What if we discovered that Venus undergoes periodic resurfacing events where the entire crust melts and reforms, as one controversial theory proposes? These discoveries would have profound implications for terraforming timelines and methods. Let's explore the cultural and psychological dimensions of choosing Venus over Mars. Mars has captured human imagination for over a century. The idea of Martians, of canal-building civilizations, of the red planet as a dying world that might once have harbored life, is deeply embedded in our culture. H.G. Wells, Edgar Rice Burroughs, Ray Bradbury, Kim Stanley Robinson, and countless others have written about Mars. It's the planet of science fiction, of adventure, of the frontier. Venus, by contrast, has a darker reputation in fiction. The planet of swamps and dinosaurs in older stories, or of acid and crushing heat in more recent science-informed fiction. It doesn't have the romantic appeal of Mars. But here's the thing. Choosing the harder, less intuitive path because it's actually better is a very human quality. When scientists and engineers began seriously comparing Venus and Mars for terraforming, many were surprised to find that Venus had so many advantages. It challenges our preconceptions. It requires us to look past the immediate surface conditions to the deeper physics and engineering realities. In a way, choosing Venus would be a statement about humanity's maturity and ambition. We're not just going for the easier-seeming option. We're carefully analyzing which path genuinely gives us the best chance of creating a second Earth. Think about this for a moment. If we successfully terraform Venus, We'll have proven that even the most hostile environment in the inner solar system can be transformed into a haven for life. We'll have demonstrated mastery over planetary-scale climate engineering. The lessons learned from cooling Venus could potentially help us manage Earth's climate more effectively. We developed technologies for atmospheric processing, solar radiation management, and ecosystem engineering that would be applicable to protecting Earth or terraforming other worlds. Venus could be a test bed for saving Earth if our own climate spirals out of control. This brings us to one of the most profound questions underlying this entire discussion. Should we terraform planets at all? Some philosophers and environmentalists argue that planets, even seemingly lifeless ones, have intrinsic value that we shouldn't violate. That the universe doesn't exist solely for human benefit, and that transforming entire worlds to suit our needs is the ultimate expression of anthropocentric arrogance. Others argue that the universe is vast and mostly empty, that creating habitats for life and consciousness is actually adding value to an otherwise meaningless cosmos, that we have not just the right but perhaps even the obligation to spread life throughout the universe if we can. These competing philosophies will shape how humanity approaches space exploration and colonization in the coming centuries. Consider also the transformative effect that terraforming Venus would have on human civilization here on Earth. A project spanning centuries or millennia, requiring international cooperation and sustained commitment across generations, would necessitate new forms of governance and social organization. We'd need institutions designed to operate across timescales far longer than current governments or corporations. We'd need to develop a cultural commitment to long-term thinking that our current quarterly earnings, election cycle-focused civilization largely lacks. The very attempt to terraform Venus might transform humanity more than it transforms the planet. Let's get specific about some of the exotic technologies that might be developed for Venus terraforming. One proposal involves aerial algae or bacteria, genetically engineered microorganisms designed to float in Venus's clouds, extracting carbon dioxide and sulfur compounds from the atmosphere and converting them into organic matter that would eventually fall to the surface, gradually removing these substances from the air. These organisms would need to be incredibly hardy, capable of surviving in sulfuric acid clouds, handling extreme ultraviolet radiation, and reproducing reliably in an alien environment. Creating such organisms would require advances in synthetic biology far beyond our current capabilities, but the fundamental principles are sound. Another technology involves molecular machines or nanobots that could self-replicate using materials from Venus's atmosphere and soil. These microscopic machines would be programmed to break down carbon dioxide molecules, sequester carbon as solid graphite or diamond dust, and release oxygen. Trillions upon trillions of these machines could theoretically process Venus's atmosphere over centuries. The challenges are enormous. Preventing uncontrolled replication that could turn into a gray goose scenario, ensuring they remain functional across many generations of replication, and powering them, likely through solar energy. This technology doesn't exist yet and might never exist in exactly this form, but it represents the kind of innovative thinking that Venus terraforming inspires. Solar shades themselves would require revolutionary materials and manufacturing. We're talking about structures with total area potentially millions of square kilometers, positioned in space at the Lagrange point. They couldn't be solid. The weight would be prohibitive. Instead, they might be extremely thin films, perhaps single molecules thick in places, manufactured in space using materials from asteroids. Or they might be swarms of smaller reflective units, each independently controlled, that coordinate to maintain the desired shade pattern. The units would need minimal propulsion to maintain position and could even be designed to be adjustable, allowing fine control over how much sunlight reaches Venus as the terraforming progresses. Here's a wild idea that some scientists have proposed. What if we used the excess atmosphere we remove from Venus to terraform Mars? If you could somehow transport the carbon dioxide from Venus to Mars, you'd solve two problems simultaneously: removing Venus's excessive greenhouse gases while giving Mars the atmospheric mass it lacks. The logistics would be absurd. You'd need to somehow lift gas from Venus's deep gravity well, transport it across tens of millions of kilometers, and deliver it to Mars. But if you had cheap enough energy and efficient enough propulsion, perhaps using nuclear or fusion rockets, it becomes theoretically possible. You could imagine a future where massive tanker ships ply the space between Venus and Mars, carrying atmospheric gases, creating a truly interconnected system of terraformed worlds. Let's discuss the biological implications more deeply. If we terraform Venus, what ecosystems should we create? We could simply try to replicate Earth's biosphere, introducing species in the same relationships they have on Earth. But we could also be more selective. Imagine a Venus with forests but no mosquitoes, with pollinators but no agricultural pests, with complex food webs but without the parasites and pathogens that plague Earth life. We could design ecosystems optimized for productivity, for beauty, for human interaction. Of course, ecosystems are enormously complex, and our understanding of them is imperfect. Removing species we consider pests might have unforeseen consequences. What seems like a nuisance might play a crucial ecological role we don't fully understand. Alternatively, we could create entirely novel ecosystems using synthetic biology. Imagine photosynthetic organisms designed to thrive in Venus's high carbon dioxide early terraforming atmosphere, growing at rates far exceeding Earth plants, rapidly converting the atmosphere and building biomass. Imagine carefully designed food webs where every organism has a specific engineered role, creating a stable, managed ecosystem unlike anything that evolved naturally. This level of biological engineering raises deep questions. Is an artificial ecosystem real nature? Is it valuable in the same way Earth's evolved ecosystems are? Would people want to live surrounded by engineered life, or would they crave the wild, unpredictable character of evolved nature? There's also the question of adapting humans themselves. If we're willing to engineer microorganisms and ecosystems, why not engineer humans to better survive Venus's conditions? People adapted to higher gravity would be stronger and more comfortable on Earth when they visit. People with enhanced heat tolerance could survive equipment failures that would kill unmodified humans. Enhanced radiation resistance would provide safety margins. But human genetic engineering is even more ethically fraught than terraforming lifeless planets. Where do we draw the line between medical therapy and enhancement? Between adaptation and creating a new species? These questions don't have easy answers, but they're worth considering because the timescales of terraforming Venus would provide ample opportunity for human evolution, both biological and technological. Here's something to consider. The first humans born on terraforming Venus, in the cloud cities, would grow up looking down at a world being transformed beneath them. They'd watch over decades as the surface cooled, as the first water appeared, as the atmosphere thinned and cleared. They'd have a relationship to planetary engineering that we can barely imagine, growing up knowing that their world was being actively created, that their children or grandchildren might walk on the surface that was still uninhabitable when they were born. This could create a culture uniquely focused on long-term thinking, on legacy, on building for the future. Or it could create impatience and frustration with a process that takes longer than individual lifetimes. The psychology and sociology of multi-generational terraforming projects is something we can only speculate about, but it would certainly shape the character of Venusian civilization. Let's talk about art and culture for a moment. Imagine the art that would emerge from a civilization living in floating cities above Venus. The views alone would be extraordinary. Vast cloudscapes stretching to a sharp, close horizon due to the thick atmosphere below, the cloud layers forming distinct stratification in different colors, the sun setting and rising over an alien skyscape. Artists would have entirely new visual vocabularies to work with. The culture that developed in these cities would be unprecedented. Humans living in artificial habitats that float freely, potentially moving with air currents, creating a semi-nomadic civilization in the sky. Cities might drift together for festivals and trade, then separate again. The cultural dynamics would be utterly unlike anything in human history. Music on Venus would be affected by the atmosphere. In the cloud layer where humans would live, sound would travel differently than on Earth due to the different atmospheric composition and pressure. Musical instruments would need to be redesigned or would produce different tones. The soundscape of daily life, the hum of life support systems, the rush of wind against habitat structures, the sounds of the clouds themselves, would create an acoustic environment unlike Earth's. Artists and musicians would incorporate these into new forms of expression. Literature would grapple with themes of transformation, of living between worlds, of the long wait for the surface to become accessible. Venus would develop its own mythology, its own cultural identity distinct from both Earth and Mars. Now let's address a crucial practical question. Where would the first landing site be once Venus's surface became habitable? Scientists would carefully choose locations based on multiple factors. Elevation, because higher elevations would become habitable first as the atmosphere thinned. Access to resources like water, ice in polar regions or minerals. Geological stability, and scientific interest. One candidate might be Maxwell Montes, the highest point on Venus, reaching 11 kilometers above the mean planetary radius. Higher elevations would experience lower atmospheric pressure and temperatures earlier in the terraforming process, potentially becoming habitable centuries before the lowlands. The symbolism of humanity's first permanent surface settlement on Venus being on its highest peak would be powerful, ascending from the clouds to the mountaintops, with a promise of eventually reaching the seas and plains. Another fascinating aspect is the preserved Soviet landers. Several Venera spacecraft remain on Venus's surface, the first human-made objects on another planet. As Venus is terraformed and the surface becomes accessible, these sites would become historically significant, preserved as monuments to humanity's first successful landings on another world. Imagine future Venusian colonists making pilgrimages to see Venera 13 or 14, ancient machines that survived for precious minutes on a hell planet, now resting peacefully in a transformed environment. These sites would be tangible links to history, physical evidence of how far humanity had come. Let's consider the geopolitical implications. Unlike the Moon or Mars, Venus is close enough and potentially valuable enough that it could become a site of serious international competition. If cloud cities proved economically viable, producing goods and energy for export, nations and corporations would scramble to establish their presence. Would Venus become divided into national zones like Antarctica, or would it be managed as a common heritage of humanity? Current space law, particularly the Outer Space Treaty of 1967, establishes that no nation can claim sovereignty over celestial bodies, but also allows for resource extraction and commercial activity. The legal framework for a terraformed Venus with permanent settlements is ambiguous at best. One possible future involves Venus being developed by an international consortium, a multinational organization specifically created to manage the terraforming and settlement process, funded by participating nations and corporations but operating independently to prevent any single entity from controlling the planet. This organization would make decisions about resource allocation, settlement locations, environmental management, and the ultimate goal state of the terraformed planet. It would need to balance efficiency with fairness, scientific goals with commercial interests, short-term pressures with long-term planning. Creating such an organization would be nearly as challenging as the technical aspects of terraforming itself. Alternatively, we might see a more anarchic development, with different groups establishing independent cloud cities with their own governance, competing and cooperating as circumstances dictate, creating a patchwork of different political systems and cultures floating in Venus's clouds. This could lead to innovation and diversity as different approaches are tried, or it could lead to conflict and inefficiency. History suggests that resource-rich frontiers tend toward conflict unless strong institutional frameworks prevent it. Whether Venus becomes a new frontier for human cooperation or competition might depend on decisions made in the next few decades about international space governance. Here's a thought that's both exciting and sobering. We might not be the civilization that completes Venus's terraforming. If the process takes thousands of years, the human civilization that begins the project might be radically different from the civilization that completes it. Political systems will rise and fall. Languages will evolve and change. Technologies we can't imagine will be developed. The people who finally walk on a fully terraformed Venus might look back at our early 21st century planning the way we look back at ancient megaliths, impressed by the ambition and persistence but barely able to comprehend the mindset of the builders. Yet the project would continue, passed from generation to generation like an eternal torch, each generation adding their contribution to the great work. This raises a profound question. How do we create institutions that last thousands of years? The longest-lasting human institutions are typically religious organizations, some extending back thousands of years with continuity of purpose, if not practice. Would terraforming Venus require a quasi-religious commitment, a sacred mission passed down through generations? Or could we create secular institutions with sufficient adaptability and redundancy to survive across these time scales? Some futurists suggest that artificial intelligence might play a crucial role, with AI systems managing the day-to-day terraforming operations while human civilization changes around them, providing continuity and institutional memory across the centuries. Let's return to the hard science for a moment and discuss some of the unknowns that could dramatically affect terraforming plans. We don't fully understand Venus's internal structure and geology. We don't know if its core is molten or solid, which affects whether a faster rotation could generate a magnetic field. We don't know the exact rate of current volcanic activity, if any. Some evidence suggests large areas of the surface are relatively young, perhaps only a few 100 million years old, implying recent resurfacing events, but this remains debated. If Venus is still volcanically active, this would continuously add gases to the atmosphere, requiring ongoing removal efforts even after initial terraforming. On the other hand, volcanic activity could provide access to geothermal energy and mineral resources. We also don't fully understand the chemistry of Venus's clouds. The sulfuric acid forms through complex chemical processes involving sulfur dioxide from volcanic emissions, but the exact mechanisms and equilibrium conditions aren't completely characterized. When we start cooling the planet and altering atmospheric composition, these chemical systems will shift in ways that our models can predict only approximately. We might encounter unexpected chemical reactions, precipitation of unusual compounds, or formation of aerosols that affect the terraforming process in unforeseen ways. This uncertainty means that terraforming Venus would need to be adaptive, constantly monitoring conditions and adjusting strategies as we learn more about how the planet responds to our interventions. Here's a particularly intriguing unknown. We don't know for certain that Venus lacks plate tectonics. Earth-style plate tectonics requires water to lubricate the process, allowing crustal plates to slide past and under each other. Venus, being dry, doesn't show clear evidence of plate boundaries. However, some recent radar mapping suggests possible tectonic activity of a different type. If introducing water to Venus triggered the start of plate tectonics, this would have profound implications. Plate tectonics regulate planetary climate over geological time by controlling carbon dioxide levels through volcanism and subduction. A terraformed Venus with active plate tectonics would be much more stable over millions of years than one without. But initiating plate tectonics might also trigger earthquakes and volcanic eruptions during a transition period that could last millions of years. Let's discuss one more technical approach that deserves attention: biological terraforming from the clouds downward. Instead of cooling the entire planet first, what if we introduced engineered organisms into the cloud layer that could begin processing the atmosphere and gradually expanding their habitat downward as conditions changed? These organisms would need to be incredibly robust, perhaps based on extremophile archaea from Earth that thrive in hot, acidic conditions. As they multiplied and spread, they would gradually alter atmospheric composition, reducing carbon dioxide and sulfuric acid while producing oxygen and potentially nitrogen compounds. Over centuries, this biological layer would expand downward, perhaps reaching the surface while it was still too hot for complex life but cool enough for these specially designed extremophiles. They would begin weathering rocks, creating primitive soils, continuing to alter atmospheric chemistry from the ground up while modified cloud organisms work from the top down. This approach has an elegant quality to it, life transforming a dead world, echoing how life transformed early Earth. It would require far less infrastructure than solar shades or massive atmospheric processing plants, though it would likely take longer. The organisms themselves would need to be carefully designed to avoid evolutionary drift that could make them less effective at terraforming or even dangerous to the eventual human inhabitants. This might require building in genetic safeguards, periodic reseeding with fresh designed organisms, or continuous monitoring and management. The bioethics of creating entirely artificial life forms specifically to die in their trillions to terraform a planet is something we'd need to grapple with, though it's arguably less problematic than potential destruction of native Venusian life if it exists. Now, imagine the moment when the first human walks on Venus's surface without being in a cloud city or floating habitat, standing on actual ground with actual sky overhead. It might be 1,000 years from now, or 3,000, or more. But whenever it happens, it will be one of the most significant moments in human history. Perhaps as significant as the first human footsteps on Earth's dry land hundreds of millions of years ago. That first person will stand on a world that was transformed through the accumulated efforts of hundreds of generations. A world that was literally hell made into a second home for humanity. The emotional weight of that moment, the connection to all the ancestors who worked toward it, the sense of accomplishment and possibility, would be overwhelming. What would they see? Perhaps a landscape of young mountains and fresh seas, with clouds of water vapor rather than sulfuric acid. Perhaps forests growing in soil that didn't exist 1,000 years before, composed of whatever organisms we decided to introduce. Perhaps cities already spreading across the landscape, built by the descendants of cloud colonists who migrated down as the surface became habitable. Perhaps artificial structures, monuments to the terraforming process, solar shade control stations that would remain in orbit indefinitely to maintain Venus's climate. They might look up and see Earth as an evening or morning star, just as we see Venus now, creating a poetic symmetry. Or perhaps what we consider the endpoint, a shirt-sleeve habitable surface, won't be the goal at all. Perhaps humanity will adapt to living in the clouds so successfully that we'll maintain Venus's surface as a managed resource zone while the real civilization remains airborne. Perhaps we'll develop technology that makes environmental suits so comfortable and capable that surface habitability becomes less important than we currently think. Perhaps we'll upload our consciousness into machines that don't care about atmospheric composition and temperature. The future is uncertain, and the civilization that ultimately makes decisions about Venus's fate might have values and capabilities we can't predict. But here's what we can say with reasonable confidence. Venus could be terraformed. The physics allows it. The engineering, while staggeringly complex, doesn't require violating any laws of nature. The resources exist within our solar system. The only real question is whether humanity will develop the technology, accumulate the resources, and maintain the political and social will to accomplish it. That last factor, the social and political will, might actually be the most difficult. Our current civilization struggles to address climate change on Earth, a problem on much smaller scales than terraforming Venus. If we can't manage our own planet sustainably, can we really undertake the transformation of another? Yet there's a counterargument. Perhaps the very attempt to terraform another planet would teach us what we need to know to better manage Earth. Perhaps the technologies developed for removing carbon dioxide from Venus's atmosphere could be scaled down to remove excess carbon dioxide from Earth's atmosphere. Perhaps the long-term thinking required for multi-generational terraforming projects would spill over into better long-term planning on Earth. Perhaps seeing Earth from the clouds of Venus would give us a perspective that helps us appreciate and protect our home world. The relationship between Earth management and terraforming other worlds isn't necessarily competitive. It could be synergistic. Here's one final perspective to consider: the philosophical and almost spiritual significance of transforming Venus. For all of human history until the last century or so, we've been bound to Earth, subject to the environment we found ourselves in. We've modified our local environment, building cities and farms, but the planet as a whole shaped us far more than we shaped it. Terraforming Venus would represent a fundamental shift. Humanity as a force capable of operating at planetary scales, not just modifying environments but creating them. It would be a coming of age for our species, a step toward true spacefaring civilization status. Carl Sagan once said that we are a way for the cosmos to know itself. life, and particularly intelligent life, is, as far as we know, vanishingly rare in the universe. The observable universe is mostly empty space, dead matter, and energy following simple physical laws. Consciousness is precious because it's the only thing we know of that can observe, appreciate, and understand the cosmos. If we have the capability to transform dead worlds into living ones, to spread the improbable beauty of life and consciousness through the solar system and potentially beyond, is there a moral imperative to do so? Not everyone would agree the answer is yes, but it's a question worth pondering. As we reach the end of this exploration, let's come back to where we started: the choice between Mars and Venus. Both are extraordinary challenges. Both could potentially be transformed into habitable worlds. But Venus, despite its hellish current conditions, offers something Mars cannot: a planet similar enough to Earth in size, mass, and gravity that it could truly become a second Earth rather than merely a human habitat on an alien world. Venus has the energy, the resources, and the physical properties to support a thriving biosphere and a civilization that could eventually rival Earth itself. Mars, wonderful as it is, will always be smaller, colder, farther from the sun, more dependent on technology for basic survival. The psychological difference matters too. Do we want humanity's future in space to be about huddling in sealed habitats on cold, dead worlds, or about creating new living worlds where future generations can walk freely under open skies? Do we want to be interplanetary survivors or interplanetary gardeners? Both approaches have merit, but they represent different visions of humanity's future. So here's the question you should ask yourself. If you could commit humanity to a 1,000-year project, knowing you'd never see the results, but knowing that your great-great-great-grandchildren, hundreds of generations removed, would walk on a living, breathing second Earth, would you make that choice? Would you begin the long, difficult work of transforming hell into paradise? Would you choose Venus? The answer might determine not just the future of Venus, but the future of humanity itself. Because the civilization that can terraform Venus is a civilization that's learned to think beyond quarters and election cycles, beyond individual lifetimes and single generations. It's a civilization that's truly matured, that understands its place in the cosmos and its responsibility to the future. Whether we develop into that civilization remains to be seen. But standing here at the beginning of the space age, looking up at the bright evening star that is Venus, we can imagine. We can plan. We can dream of the day when that brilliant light in our sky is not a warning of how planets can go wrong, but a promise of what they can become with time, effort, and the accumulated wisdom and will of countless generations working toward a common goal. Venus awaits. The choice is ours.